Today's topic is specifically simulation premium, and our agenda today, we start out with why do we want to simulate. It kind of became obvious to me when I started getting into the world of analysis that this is something that's only going to expand as time goes by. Solvers get more efficient, hardware gets faster, and SOLIDWORKS has really created a niche market of simulation for the everyman, for the designer. It used to be that you could only simulate if you spent a lot of time in a dark room somewhere banging away on a computer, but now we've made it a lot simpler. And with Simulation Premium, we're going to see today that some higher level analysis really aren't that much of a switch from doing basic linear statics. Next, we're going to look at a plastic palette example today. And we're going to start out with a linear static design optimization to get the geometry kind of where we want it. And then we're going to look at different types of analysis and adding detail to that model with more accurate material models, dynamic tests, and a creep analysis in addition. And then we're going to wrap things up with an example of 2D simplification with a hyperelastic material model. And then we can take a peek at what it looks like to do composites analysis in the Simulation Premium product. So why simulate? This is my favorite why simulate slide. The cost of change goes much higher as time goes by. Prototypes are a lot more expensive to change than a CAD model. A production tool is certainly far more expensive to manipulate than a soft tool. And the more we know about our designs up front, the more knowledge we have, less effort is taken to optimize that design. Putting it another way, I call this a napkin sketch ROI. We can get into a lot more detail with time value money, but really, if you sit down and think about it, a typical physical prototype testing, it might take us a week to kick off our first prototype and a couple $1,000s in hardware and $800 in labor. And every design iteration is going to take time to manipulate our prototypes, time to run the testing. And so in our physical example here, we're looking at two weeks of time and almost $11,000 in costs. The virtual prototyping method, before we've created physical prototypes, we're looking at just labor cost, 4 hours or so, let's say, to set up an initial model. And every time we make a design change, the cost of reanalyzing is going to be pretty low, and you're going to see with the optimization tool, actually running multiple iterations can take quite a bit less than 2 hours in many occasions. But when we sum it all up, we're looking at 2 days of time versus 2 weeks, and $1,600 versus $10,600. And this is something that if you're thinking about investing in some sort of analysis or simulation tool, sit down and do the napkin sketch. Does it make sense for you to invest $4,000 to $14,000 in the simulation package? And odds are it probably does make sense. There's another benefit, not just time and cost, but physical versus virtual prototyping. When we physically test something, we need to outfit it with sensors and measure the data, and we can't always get out the data that we want. But with a virtual test setup, we can pretty much query the model anywhere to get the data that we desire, and not to mention the lead times and the physical intrusiveness of just setting up a physical test. Sometimes we manipulate the test in progress by trying to take the data. So the product that we're going to concentrate on today is the Simulation Premium package, which is the large gray block in the center of your screen. So that encompasses all the capabilities in Simulation Professional, in addition to the nonlinear analysis, composites, and dynamic analysis of Simulation Premium. We also have flow simulation, which is very often used for thermal concerns, in addition to flow analysis, such as pressure drops and lots of these distributions. We have injection molding simulation, which is our SOLIDWORKS plastics tool. And then we also have environmental simulation, or sustainability tool, which is outputting essentially the eco footprint of your design. So to get started, I'm going to look at our palette, and I'm going to call this phase 1, and we're going to do a basic linear static analysis of our palette, and then we're going to do a design optimization to reduce the mass and keep the factor of safeties at a reasonable level. And then we're going to move to the next steps and start adding more detail to the model. So phase 1 we could get accomplished actually using the simulation professional tool. And today I chose to work on a plastic palette because dunnage, returnable dunnage is very popular these days, and we can create a more durable palette that's not going to wear and create splinters and cause problems. And so how do we get started? Well, let's start with the existing simulation model in here. And the basic outputs from all structural simulation are going to be stresses, displacements, and then also factors of safety. And what is in this model? Well, we've got these nice icons here that tell us what's going on in the simulation. And we have a feature manager that is driving the simulation, and it's pretty much a top-to-bottom process. So let's start at the bottom. Stresses, strains, displacements, factors of safety are a typical output. We have 5,000 pounds evenly distributed across the top of our palette. Everything in here, just like SOLIDWORKS, is a right mouse button to see what's going on. So I've selected this entire top face and told it I want to put 50,000 pound force on here. This is a static analysis, so we're assuming that that happens slowly. And then I have my palette fixtured. And let me cut a little section here. And I'm assuming that the skids of the forklift are not 100% underneath the pallet. So we have a fixture on the faces where the skids might be. And in this case, it's a roller slider fixture. And we get nice visual feedback at how we're holding onto the part. So in this case, it's a roller slider, and we have an animation that shows me what that means. I can also fix the geometry. And if these were cylindrical faces, I could use something like a fixed hinge. Any way you want to retain or restrain your part, we have standard fixtures and advanced fixtures that we can use to take care of that. And then as we walk upwards into our material or into our model, we see that we have a body that represents the palette, and we have a material definition. And once again, with our right mouse button, we can apply edit materials. So anything in blue is a custom material here, and I actually created one for this model because we're going to use nonlinear material properties at a later date. But we also have a pretty wide array of pre-existing materials, and creating a custom material can be just as simple as copying an existing and bringing it down into our blue libraries and pasting. And now I can make changes to that model. So the basic model setup process, we have our command manager with all our fixtures and forces and constraints, and then looking at how to look at our results once they're created. Many are duplicated over here in the feature manager. But just starting a new study, we have our whole selection, which we're going to start with the linear static, and I just want to show you the basic test setup. It's really a pretty quick process. Apply, edit material properties. I'm going to use my custom plastic material. This is a polypropylene 40% glass fill. It's pretty rugged, and I'm going to choose the linear elastic material model here to start out with. So we get a check mark next to our little solid here. It tells us we're ready to move to the next phase. I don't need to define any connections because this is one big chunk of a part right now. But if I had multiple bodies in the model, I can connect them with bolts, welds, spot welds, in contacts to bond or allow bodies to not pass through each other. I'm going to fixture this, so we'll start with the roller slider, and I'll pick my split faces to represent where the skids for the lift are. So we're not fully supporting our pallet. And then now I need to define some external loads. We have forces, torques, pressures, gravity, but I'll start with just a force evenly applied across this face. In the next phase in doing any kind of simulation, it's called finite element analysis because we're breaking up our model into little finite elements, and we call it the meshing process. And we have a really great auto mesher that works pretty flawlessly. So we just mesh, and then we can solve the study. And the solve time on this is only a couple minutes. So let's jump over to our completed model and review our stresses. So we'll start with factor of safety, because if we have multiple materials in the model, they might have different limit stresses for the material. So that's why our factor of safety plot has been created. It divides the stresses on the part by the limit stress and tells us how close to a factor of safety we are. So we're down to a 1.2, which is pretty low. And we want to look at this anytime that we have a plot on the screen. If we right mouse button, we're going to have options for querying that plot or manipulating that plot. So let's say I want to probe and read the factor of safety as we walk across a section of the model. So I can start here and walk my way down the model and across the spots of high stress, and then I can do a quick plot and see how the stress varied as I walked across my path. In this case, this is the factor of safety. We're down to a minimum in this location of a 2.5 and going up to 15. So let's take a look at our average or von Mises stresses. And we have the deformation scale is bumped up a little bit. But if we want to know where the stress is at in the model, so we can see the outside, but we can't really get to the inside. So we have a couple ways of manipulating our plots. We have ISO clipping, which is very nice. So this is going to only show me stresses above and below a certain value. So anything over 23 megapascals is going to show up. And the limit strength for this highly glass-filled polypropylene is pretty high. It's about 100 megapascals or so. But we can see that most of the stress and deformation is being generated, when the skids have stopped supporting the pallet, and then we still have some mass around the edge of the pallet that's causing our bending stresses in this location. So when we're looking to remove material from a part, the ISO plot can be very handy for figuring out what part of the structure is not being loaded up. So this is all fine and dandy. So this is one iteration of the simulation. But let's say now I want to start pulling mass out of the product, because mass is essentially money. And any feature, parameter, or sketch dimension can be used to drive a design study or a design optimization. So I'm going to jump over and start up a design study. And the first thing that we can do in our design study is we need to define parameters or variables that we're going to modify. And in the case of this model, I'm manipulating the wall thicknesses in addition to the top layer thickness in the model, since we are supporting the pallet for this low case with the forks underneath and applying the loads. The thickness of the top is a pretty critical factor. So how do I create these variables? Well, I'm in my design study, variables, constraints, and goals, and I can say I want to add a new parameter. These can be model dimensions or simulation inputs, and you see right away, once I'm in this mode, it shows me all my annotations, and I can just select that annotation, and it links it to the model. I give it a name, and now this is a variable that I can use to manipulate my model. So that's where I get my inputs. Where do I get my constraints? Well, the constraints are the feedback to the design optimization or sensors. And these are both simulation and CAD entities. We can look at mass properties of the model. We can look at simulation data, such as stress or displacements, and we can ask for them over the model max, or we can ask for, say, maximum displacement over selected entities, such as a face. And then lastly, we define goals. And so what I've already created, it's been in the oven at 350 for 45 minutes already, is an optimization study where I'm rerunning the vertical load test with the skid underneath the pallet. And we've gone through 4 different scenarios. And as I walk through the different scenarios, you can see the model is automatically updating. If you're familiar with design studies in SOLIDWORKS, you've probably done this before to just check your CAD designs. But with each one of these different scenarios, we have rerun our stress test. And we started out with a initial model of 116 pounds. And I want my stress to be under 100 megapascals, or I could conversely say, I want my factor of safety to be greater than 1. And I'm telling the solver, I want to choose the design with the least amount of mass. And I'm varying the vertical thickness of my top layer and my wall thickness in these bosses inside the pallet. And what have we come up with? Well, we've got design 3 with the thicker top, and we're down to 97 pounds. Our factor of safety has met our requirement. If we look at some of the other scenarios, we find that we're extremely sensitive to the thickness of this top section here, where the stresses just skyrocket if I keep it that thin. And in the setup here, I just asked for 2 inches and 3 inches, and then 2 different wall thicknesses. But we can also increase the number of variables and try different scenarios. But for the rest of my simulation, I'm going to use this the green column here, the optimal design, and I'm going to use this to start looking at some of the capabilities in the simulation premium. So essentially, this design optimization could be done inside of a Simulation Professional because we used a linear static analysis. I mean, the analysis is happening slowly, and the material properties are assumed linear, which we're going to talk about in just a couple seconds.